Can you hear me well? Okay. Thank you very much. Thanks for the presentation and thanks for the invitation. It's a great pleasure to be here. This slide is a bit mysterious, it's not intentional. I meant to have some text in there, but I chose some very fancy font, which was not recognized by Adobe. So you will never know what was meant to be there. So part of my research is about understanding the local arithmetic of curves. So given a curve, what is its behavior over QP, say for some prime P. And in this talk, my aim is to give a broad overview of how it fits in the bigger picture of solving Diophantine equations. I'll explain why it is so important to understand local arithmetic of curves in this big question of solving Diophantine equations. And I'll explain why. I'll explain how one can use the local knowledge that we have to understand some global questions, such as the rational points on the curves, from the QP points on the curves. And then I'll give some applications, some theoretical and computational results that can be applied in this method. So, okay, I'll use this. Okay, so the bigger picture, as I said, is solving Diophantine equations. And my first question is, how good are we at solving Diophantine equations? So if I give you a polynomial equation in n variables with rational coefficients, how good are we at randomly solving it? So for example, these are 4 random equations, and I let you have a quick go at it. If you had to solve, so if you had to understand the rational solutions to these equations, what would you do and how fast could you do this? So for some of them, you may be able to find a trick and actually answer this positively. So that might be fast. But for some of them, it's going to take a while and you may not succeed at all. So this is around a question that was posed by Hilbert in his address in 1900, when he posed his problems, his famous problems, and this was the 10th problem. Given a Diophantine equation with any number of unknown quantities and with rational integral numerical coefficients, the problem is to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. And the answer was given 70 years later, building on work of Robinson, Davis, and Putnam. Matiaszewicz was able to say that there is no such a process. So it's not true that you will be able to find an algorithm that will solve in the rationals a random Diophantine equation. So this is where understanding the local behavior of your equation comes very handy. So here is an example. If I give you this equation, and I want to know if there is a rational solution to that, then you may have 2 reflexes. The first thing you may do, and probably you will do, is to compute the discriminant of that quadratic equation, and then you'll find that it's negative, which means that it doesn't have a solution over R. And because Q sits in R, you also know that there is no solution over Q. You could have, instead, chosen a prime P, in this case it may be 5, and instead of working over R, you will work over FP. So you choose 5, and then you try to understand if there is a solution, modulo 5, to this equation. Then very quickly you find that there is none, simply because you have so many numbers to check with. And because you have no solution modulo 5, you know that you have no solution over the 5-adic numbers. And again, Q sits inside Q5, so you can conclude that you have no rational points. Okay, so we've kind of understand that it's easy to work with local fields. And the question I want to discuss is this local understanding we have of varieties. When I say varieties, I mean the vanishing of finitely many equations. So I may be interested in one equation, but I may be interested in many. If this is the case, then I talk about solving or finding solutions of a variety. So we have a pretty good handle of local theory of varieties over QP over R, and our aim is to understand their global arithmetic, so over Q. Everything I'm saying here works for global fields and local fields, but I'm going to stick with Q just for the purpose of this talk. So that's this arrow. We want to understand how can we use what we know over local fields to understand the global arithmetic of the curves, the varieties. So we want to understand their rational points, say. Okay, so there are ways, and I'm going to present 3 of them. So 3 bridges from understanding the local properties of varieties to understanding their global properties. And the first one is probably the best you can hope for. It's this local global principle, or the Hasse principle. So we've seen with this quadratic equation that if you check if it has solutions over R and over QP, if it turns out that it doesn't have a solution over R or over QP for some prime, you know it doesn't have a rational point. So is the reverse true? And namely, if you find that your equation has everywhere solutions for every QP and R, does it mean that it has a rational solution? If it is the case, then we say that it satisfies the local global principle, or the Hasse principle, which is the best case scenario, because we do know how to prove, for example, it is possible to prove that an equation has points over QP for all primes and R. So if we could use this, then that would give us a solution over Q. So what type of curves satisfy these properties? In terms of curves, smooth projective curves of genus 0 do satisfy the local global principle. Those are conic sections, which are represented here. And in addition, for those curves, if it turns out that there is a solution, then they have infinitely many solutions, and we can parameterize those. So in terms of solving the equation, this is complete. You find whether you have a solution of a Q, you find a parameterization, and you've entirely described the rational solutions of your equation. Okay, so this is for genus 0 curves. I'm going to jump to genus 2 and higher. So if you have a genus 2 curves, the example here, for example, this is y squared is any polynomial of degree 6 will do. If you have such an equation and you want to understand its rational point, maybe the first question you can ask is how many are you expecting? Is it like genus 0 where you have infinitely many? Do you have finitely many, or do you have a mix of both? And the answer was given by Foltings in 83. If you have a smooth projective curve of genus 2 or more, defined over Q, again this works over number fields, then the set of rational points is finite. So when it comes to solving equation, maybe you're happy with this. Maybe it's enough for you to know that you only have finitely many solutions and you don't want to know the solutions. But if you do want to know the solutions, then you could try to just search for solutions. But if you don't have an upper bound, then you will never know whether you found them all. So this is where this second bridge comes in. This is Chaboty and Chaboty method, quadratic Chaboty as well, and Coleman theorem. So the first thing is the theorem of Coleman. Under some conditions on the prime that you choose, the prime P and your curve X, and I won't give any details here, the set of rational points of your curve is bounded above by the number of points on your curve over Fp plus twice the genus plus 2. So this gives you literally a bridge from your knowledge of the curve over Fp to the knowledge of the curve of a Q. And again, you may still search for points and then stop when you've reached the bound, but if you want to explicitly produce those points, those rational points, this is the method of Chaboty, which allows you to use what's called Kalman integrals between QP points of your curve. And there is a vast body of work. Again, I will remain very vague here, but the point is you can integrate between two QP points and determine whether this QP point is a rational point or not. So again, this is a very strong occurrence of your knowledge of QP points leading to the knowledge of Q points on your curve. I should say that I will talk about many topics in this talk, and I checked the abstract of this conference, and almost, if not all of them, are talked about in the afternoon session. So if you need any detail of any of this, you should be able to find an expert in the room to answer your questions. Okay, so this was the second bridge for genus 2 and higher. And then I left out the genus 1 curves, especially because they behave very differently. So we've seen that genus 0 has infinitely many points, genus 2 and more have finitely many points, and straight in the middle sits the genus 1 curves. So you have two ways to deal with the genus 1 curve. The first one, if your genus 1 curve has a rational point and you are aware of it, so if you know it has one, then you have an elliptic curve. An example of which is this one. So you have y squared is a cubic polynomial. Because you have this rational point, you have what's called a dimension 1 abelian variety. This elliptic curve, equipped with this rational point, has a structure, a group structure on its set of rational points. And of course, we are going to exploit this structure to understand all the points. And this is doable thanks to a theorem of Mordell, which tells you that the set of rational points is not only a group, not only an abelian group, but it's a finitely generated abelian group. So in particular, the problem of solving elliptic curves now breaks down into two problems. The first one is to understand the torsion points, points which when you add them to themselves eventually go back to the identity point. And then the free part of your abelian group, which is given by this rank of the elliptic curve, so namely the number of generators you need to completely produce your rational points. For example, if I give you the rank of this elliptic curve, I tell you it's 2, then you're going to search for 2 points. You're going to prove that they're linearly independent, they have infinite order, and that's it. You can hand me those 2 generators, and I will understand completely the rational points of that curve. The torsions has been dealt with over Q by a very deep theorem of Mazur, so we also understand the torsions of elliptic curves. Okay, so this is if you are given a genus 1 curve with a point. What if you have a genus 1 curve but isn't clear whether it has a point? So here you need to first check over local fields whether it has a point. If it doesn't, then it doesn't have a rational point and you're done. But if it does have a rational point over all QP and R, then you may or may not have a counterexample to the Hasse principle. So it is possible for genus 1 to be everywhere locally soluble, namely have a QP point for all P and an R point, and yet fail to have a rational point. And the question of understanding whether it's the case is a very hard problem. So what we do in this case, you take your curve C, the one you try to understand if it has a rational point, and you link it to an elliptic curve. This elliptic curve, it's called its Jacobian. And then if you want to understand if you have a rational point on your initial curve C, you study the Jacobian. So we're back to square one, where we need to study an elliptic curve in both cases. And this is where the bridge comes in. This is the Birch and Swinnerton-Dyer conjecture. So in the 60s, Birch and Swinnerton-Dyer started some numerical experiments to try to understand if there is a link between the rank of elliptic curves and what's described here as an associated zeta function near the point s equal 1. So I believe you've seen L functions quite a few times already. And I will yet again give you yet another definition of an L function, the one that I like, especially because it clearly shows this bridge between local and global. So the L function associated to an elliptic curve over Q can be given by an Euler product. So it's very much a local global object. At each prime P, the data you need to compute is this little AP, which is essentially given by the number of points that your curve has over Fp for all prime P. So you compute this, and you obtain your L function, and BSD, the first version of their conjecture, asserts that the rank of your elliptic curve is given by the order of vanishing of this L function at s equal 1. So again, let me emphasize that it's very much this local to global bridge where you started by computing number of points over P, over Fp, and then you get the rank, which is a global object. Namely, how many generators do you need to completely understand the rational points on your curve? Okay, so if we knew BSD, which we don't, we understand rank 0 and 1 pretty well over Q, but in vast generality we don't. But in this talk I will assume that we understand everything. If we knew this, then we could very nicely, completely understand the rational points of elliptic curves. But what if you were given this maybe counterexample to the Hasse principle? So you had this genus 1 curve and you didn't know whether it has a rational point. You linked it to its Jacobian, which is an elliptic curve. And when you do this, what is happening is really that your curve C is now isomorphic over QP for all prime P to its Jacobian. And it's also isomorphic over R to its Jacobian. And the question you're asking, if you want to know if your genus 1 has a rational point, is whether it is isomorphic over Q to your elliptic curve. Because if it is, then this isomorphism will translate your rational point from the elliptic curve to your genus 1 curve. And this is linked to a very interesting and vast topic, which is the study of the Shafarevich-Tate group of elliptic curves. So in my example, curves that are isomorphic over all completion of Q to your Jacobian or your elliptic curve, they form a group, which we believe is finite, but it's unproven, which is called the Shafarevich-Tate group of that Jacobian or that elliptic curve. Studying this group is very, very difficult. Equivalently, studying this isomorphism over Q between C and its Jacobian. So when you ask the question whether C is isomorphic over Q to its Jacobian, what you really ask is whether C is the trivial element in the Shafarevich-Tate group of its Jacobian. And here again, I should repeat this, understanding even computing elements of SHA, of this Shafarevich-Tate group, is quite difficult. So here again, the Birch and Swinnerton-Dyer conjecture can be used if we knew, and many of us actually consider the second version of BSD as a way to compute the order of the Shafarevich-Tate group. So what it says, not only it says that the order of vanishing of the L function at s equal 1 is the rank, but it also says that if you take this L function and you take its Taylor expansion around s equal 1, then you look at the leading term of that expansion, and what you see is this product of invariant of the curve. And the reason I say that we can use this to understand the order of the Shafarevich-Tate group, assuming it's finite, is because we have a pretty good handle of the rest. So this is the real period of the elliptic curve, which we understand it's basically the knowledge of your elliptic curve over C. And these little fudge factors, they are local fudge factors, they're indexed by the primes p. They kind of measure how bad your elliptic curve behaves over QP. And we understand them really well. And of course, the torsion squared here. The regulator is related to the generators of the Mordell-Verre group. If you're given generators, we can easily compute this regulator. So in fact, you can see, and that's what I will do, you can see the second version of BSD as a way to solve for the order of Shah, because the rest we can compute. And in particular, when you try to understand if a curve, a genus 1 curve, is isomorphic over Q to an elliptic curve, if, for example, you use BSD and you find that the order of Shah is 1, then you know that necessarily your curve has a point. Okay, so these are the three main bridges. There are more, but I won't discuss them. These are the three bridges that I wanted to present. So we've seen the local global principle for genus 0, Chabot method and Coleman's theorem for genus 2 and higher. And then we've seen the Birch and Swinnerton-Dyer for genus 1 curves. But I should mention that BSD is not only for genus 1. It's actually, genus 1 is just the dimension 1 of abelian varieties, and the Birch and Swinnerton-Dyer is really a conjecture about abelian varieties. So why is it that I stick to curves? How come that I kind of claim that I can use curves to understand abelian varieties? It's because of the following fact. Given a curve of genus 2 or more, they are not abelian varieties. There is no group structure on them. But as I've done for genus 1 curves, you can always associate a Jacobian variety to a curve C. And when you do this, you do obtain an abelian variety. So this Jacobian variety is an abelian variety, and in general, if you give me a curve of genus n, then I will be able to associate an abelian variety of dimension n, namely it's Jacobian. And the reason I'm so interested in curves is because of the following. I could decide to take my abelian variety and study it from its defining equations. But let me give you an example in genus 2 of what the Jacobian looks like. If you take y squared is f of x, and f of x is going to be a degree 5 or 6, then you have a genus 2 curve. And you associate an abelian surface, it's Jacobian. If you want to study it in terms of Dyer-Fontein equations, you're going to have to stare at 72 equations in 16 variables. And that's a lot. Some people do that, and it sometimes works, but it's difficult. Instead, thanks to a large body of work, we can claim that the local arithmetic of the Jacobian, this dimension n abelian variety, can be extracted from the local arithmetic of the curve, the underlying curve. So for example, if I want to compute the L function of the Jacobian of the genus 12 curve, it's enough for me to understand the local arithmetic of that curve of genus 12. It's the same for the Tamagawa numbers, and it's the same for quite a few arithmetic invariants as well. So it's really why I'm really trying to understand the p-adic theory of curves, because it also gives me information on local and then global arithmetic of Jacobians when I use the bridges I presented. Okay, so hopefully now we understand why we would like to understand a good p-adic theory of curves. So what do we actually want from this theory? We first need this theory to control the p-adic geometry of the curve. We have to understand how the curve behaves over QP. We need it to be applicable to arithmetic problems, such as BSD and Chabot, because we want to use those bridges to then conclude on global arithmetic problems. And then ideally, we'd like them to be computationally accessible, simply because one way to work around those those problems of solving equations is to generate data, to maybe guess patterns, or sometimes check patterns, which is, if you want to think about BSD this way, it's really the way it came about. There was data, they generated data, they looked, they checked, and they conjectured that this rank was visible in the order of vanishing of the L function. So we really want this p-adic theory to have some computational accessibility. And for which type of curves do we want this p-adic theory to work? Well, namely, all of them. So elliptic curves to start with, but this is well established. Hyperelliptic curves, which I will describe. This is very recent, well, moderately recent work. I'm going to use elliptic curves to introduce the method for hyperelliptic curves, and more generally to general curves. So you may notice that elliptic curves and hyperelliptic curves, they're very similar looking and they're very nicely presented. Namely, just a polynomial of some degree will define the curve for you. General curves are, of course, a bit trickier. This is an example of a genus 3, which is not hyperelliptic. And as you can see, the model with which it's presented is a bit more involved. So we may expect some difficulties for general curves because of this. Okay. Let me start with elliptic curves, and I should warn the experts in the room. What I'm going to say is very elementary and probably not the best way to present local arithmetic of elliptic curves, but this is because I want to use this method to go on with hyperelliptic curves. So there is a reason behind this. So I will ask you to bear with me a second. All right. I have an elliptic curve and I'm trying to understand the minimal data that I need to compute its L function. So if you remember, to compute the L function of an elliptic curve, I need to generate these little APs at all prime p. So for this, let's take an example. I'll choose an elliptic curve. Because I'm going to reduce mod p, I clear denominators and I present a model over z. So my roots, which is really the data of this elliptic curve here, alpha 1, alpha 2, alpha 3, they completely determine my elliptic curve, and they're defined over z. It's an elliptic curve, it's smooth, it looks like this, or maybe it has an egg and another one, it depends on the roots. Okay, so we understand, if you remember, this AP has to do with the number of points over fp. So you reduce your elliptic curve mod p, and then three things can happen. It may be that the three roots reduce to the same, it may be that the three roots reduce to three different elements over fp. Namely, this curve here over fp is still an elliptic curve, it's still smooth. It may be that two of your roots collapse to the same element. Say you work over f5 and your roots were 1, 5, and 10. Then you have a nodal curve over fp, and in this case, it's essential to understand whether the slopes of the tangent of the node are defined over fp or fp squared to be able to understand AP. And the third thing that could happen is that your three roots, mod p, reduce to the same element. Say your roots are 0, 5, and 10. Okay, if you know those three informations, plus whether your tangents are defined over fp or fp squared, I claim that you can compute the AP value. So what do we need to know to understand which one it is, which case we are in? The first guess could be the discriminant, because the discriminant by definition understands the difference of the roots. So if the discriminant is divisible by some prime p, it's because two of the roots will collapse mod p. So discriminant is really good at telling you whether you have good or bad reduction, namely whether you are in this situation or if you are in one of those two. But it does not distinguish between the two ones. So the discriminant is not enough if you want to understand the AP value and construct the L function. Instead, I claim that if you knew the reduction of the roots mod p, it would be enough. It's clear because it will give you the picture, definitely. And then, this is a claim that I make, you will also understand whether your slopes are defined over fp or fp squared. So in that case, the minimal data that you need to completely understand this AP value is only to understand the reduction of your roots mod p. Okay, this is a picture of the Kodaira classification of elliptic curves. This comes from the Arithmetic of Elliptic Curves, the book by Silverman. And the beauty of elliptic curves sits there. There is a very neat and nice and short classification of everything that can happen over QP. You are either in the first column, you have good reduction, or the rest is bad reduction. And I guess you could say that it goes worse and worse. And if you want to completely understand the local behavior of your curve, you need to understand in which column you sit, and also you need to understand a few more elements, namely, in this case, you'd like to understand what n do you have. And to do this, again, I will claim it, but the minimal data that you need to know exactly the local behavior of your curve is, as we've seen, the reductions of the roots, but you also want to actually understand the valuation of their difference. This is what will give you the little n that is here. And if you want to push this a bit further, if you want to understand a bit deeper, you will need also to understand how Galois or inertia acts on the roots of your elliptic curve when they are seen in QP bar. So for elliptic curves, if you have this minimal data, then you completely understand their local behavior. Okay. Maybe a few words, because we're talking about how the local behavior tells you about the global one. What do you do with this classification I showed you? So how this very good understanding of local behavior of elliptic curve help us to understand the global arithmetic of elliptic curves? One example that I will use is that of the parity conjecture. BSD tells you about the rank. The parity conjecture tells you about the parity of the rank. And one thing that I should say is that it's possible, under some hypothesis, to compute the parity of the rank via local data. So in particular, if you know the classification I showed you just before, you can compute the parity of the rank. That's very handy, simply because sometimes, if you want to understand the rank of an elliptic curve, you can use many algorithms, and you may end up with bounds. You know that the rank is more than 1 and less than 2, but you just don't know if it's 1 or 2, then you can use parity to decide if you knew this. And then, of course, you may want to prove that BSD actually correctly predicts the parity. And that's called the parity conjecture. And here again, the fact that we know this classification has allowed other researchers to prove the parity conjecture for elliptic curves in certain cases. So this is very much a global application. Another one that I should cite, which does not appear in the bridges but should somehow, is beyond elliptic curves when it comes to Fermat equations. So Fermat's last theorem has been proven using elliptic curves, and within this there is a method called the modular method, which allows you to solve or find that there is no solutions to Fermat equations. And one of the steps is to compute a local invariant of elliptic curves. So here again, our knowledge of the local arithmetic of elliptic curves is used to prove global results. And then, of course, the computational aspect of this, TESS algorithm is an algorithm that you can run on the coefficients of your curve that will get you in which column you sit in the classification I showed you. And since we have this algorithm, then it has been implemented and we now have vast databases with which we can play. Okay. So that's the story for elliptic curves, and this was well established. And I'm going to use this to extend this approach to hyperelliptic curves, you can see that they are not so different. I mean, basically you have y squared is a cubic, and you go to y squared is a degree n polynomial, and I'm going to claim that the knowledge of the roots mod p and the valuation between the roots that we've seen for the elliptic curves works as well for hyperelliptic curve. So what we are going to do is to study the p-adic distribution or p-adic clustering of our roots. So let me give you an example. This is a genus 3 hyperelliptic curve, and again I will present it to you as a bunch of roots. The roots could live in QP bar. In my example, they're just over ZP. And I'm going to be interested in their differences, the valuations of their differences in QP. So let me extract the roots. The first 5 that I extract, they're all very close to 0. You've got 0, p squared, 2p squared, 3p squared, 4p squared. Then you have I and minus I, which p-adically are far away from 0 and far away from each other, simply because the valuation of their difference is not divisible by p. Then you have 3 roots, which are clustered around 1, and some of them are closer, and one of them is a bit further apart. So the data that I want to record is quite a few things, but the first thing I'm going to do is I'm going to draw p-adic circles around this. So the first I will draw is this p-adic disk of radius 0. And this is the minimal distance between the roots, all of them. For example, we saw that the difference between I and 0 is not divisible by p. So the minimal radius of this p-adic disk is 0. And then I can go deeper, and I'll find a smaller p-adic disk, this time of radius 2, because of the differences of those roots. I'll find then another one of radius 2, and then a smaller one of radius 3, because 1 and 1 plus p cubed, their difference is divisible by p cubed. Okay, and here it is. The minimal data that I want to record to understand the local arithmetic of my hyperelliptic curve is the minimal distance between the roots. I want to understand the size of those p-adic disks, which I will call clusters. I want to understand namely if there is an even number of roots or an odd number of roots inside. And I want to understand how they are contained. I want to understand how they are interlinked. If I had a leading term, which I don't, but if I had one, I would like to understand the valuation of the leading term. And I would need also, to some local arithmetic invariance, I would need to understand how inertia acts on the roots when they're defined over QP bar. So this is the equivalent of the minimal data that I had for elliptic curves. But of course, I need to present it in a different way for hyperelliptic curves, because the way my roots can collapse, because they have so many more roots, it's a lot more involved. So I need to capture this clustering in one way or another, and this is what I'm going to do. So that's a work joint with Tim and Vladimir Dokshitzer and Adam Morgan, which concerns hyperelliptic curves over local fields. And I should emphasize that this works when the residue characteristic of this local field is not 2. It's very much for the expert, this slide. It's just kind of a summary of everything that you can extract from the cluster picture. And I'll go quickly over it, but you can extract the reduction type and the reduction type of the curve, and most importantly of its Jacobian. Because if you remember, before everything, for higher genus curves, we're really interested in the arithmetic of the associated Abelian variety, its Jacobian. So clusters let you do this. Then you can extract explicitly a regular model when it's semi-stable. The conductor exponent, which I mentioned, is used in the modular method. The Galois representation, when you work over QL, which is not P. Thanks to the work of Faraghi, we can now understand whether the curve has a point over QP, given the cluster picture, in some cases when it's tame plus some conditions. And the work of Betts also gives you a closed form formula for the Tamagawa numbers. Those are the little fudge factors that I showed you in the second version of BSD, which was easy to access for elliptic curves, but a lot more challenging for Jacobians. The differentials as well, thanks to Kurzweiler when it's semi-stable. The root numbers, work of Bissat when it's tame. And Faraghi-Nowell also gives you an explicit description of the strict normal crossing model from the cluster picture when it's tame. And Best and Van Bommel have implemented this, and clusters now appear in the LMFDB. Okay, so to summarize, we went from a very complex object, which is a hyperelliptic curve over a local field, and we've just captured some finite combinatorial data, this cluster picture. And then there is this cluster picture machinery, which I haven't said anything about, which relies on quite a lot of work and quite a few theorems that let you extract the local arithmetic of the curve and its Jacobian. And then you use your bridges and you can access the global arithmetic of the curve and the Jacobian. So I emphasize the fact that it's combinatorial. Namely, if I give you a genus G curve, then you have a finite number of roots, which then can form finitely many clusters. So that classification is for genus 2. And I think, yeah, for genus 2. You may imagine that it will grow enormously as the genus grows, right? But nevertheless, this is a classification and it will come very handy. And then a very fun thing that you can do, you can reverse engineer the whole thing. You may start with a wish, maybe you want your genus 2 to be non-semi-stable over QP. Then you use the fact that we have a semi-stability criterion on the cluster, and you design a cluster which faults this semi-stability criterion. So typically, that picture fails to be semi-stable. Then you just have to find a curve, or a family of curves, which satisfy this cluster picture. So that's one example. Here, for each p bigger than 5, you will get a genus 2, which is not semi-stable over QP. Okay. Maybe it's best illustrated if I give you a few examples of how do we use this machinery to access global and computational applications. So I'll present a few of them, the ones that I've talked in the bridges. So an example of verifying BSD, theoretically, like a theoretical evidence that BSD is true for elliptic curves over totally real fields and abelian surfaces that are principally polarized, namely Jacobians of genus 2. And then an example which is, oh, I should mention, the first one is joint work with Holly Green and Vladimir Dokshitzer. And the second example is a work of Betts, Duque, Rosero, Hashimoto, and Spelier, where they use cluster pictures to understand the local height on hyperelliptic curves, which is a very important ingredient in the quadratic Chaboty method. So this comes with the second bridge I presented. And then a more algorithmic aspect of this work is the work with Drew Sutherland, where we compute the factors at primes of almost good reduction for genus 2. And then an application in families of curves, so this modular method I talked about, where we compute conjecture exponents, and this is joint work with Martin Azon, Mar Kurko-Ranzo, Malea Kawaja, and Diana Mokanu. And the last one will be an example of this reverse engineering that I talked about, which is a work of Annie and Dokshitzer, and they explicitly construct hyperelliptic curves which have a specified Galois image. Okay, so The first application is theoretical and it uses the classification. So here, what we're after is proving that BSD correctly predicts the parity of the rank. And we do this in the case of elliptic curves, and then later on we do this in the case of Jacobians of genus 2 curves. So what I show here is our approach. Basically, once you've computed the parity of the rank out of local invariance, then you want to prove that BSD correctly predicts whatever this parity is. And to do this, we do a case-by-case analysis. If the elliptic curve looks like this over QP, and another elliptic curve looks like this over QP, then this is what's happening, and then this is the cluster machinery telling you what is the local behavior of those elliptic curves. You do this for all cases, and then you've proven your theorem. And that's the same for genus 2, except there are more cases. So of course we use quite a few tricks, because if you really needed to cover all cases, it would be very long. So you can actually just prove some cases and then use some tricks to extend to all cases. So that's an example of the use of the classification. Given a genus, you have a finite number of possible cluster pictures to look for. The second, this is a screenshot of their paper. So this is this quadratic Chaboty, where here they really use the core of the cluster picture machinery. Namely, they use that the cluster picture really understands the p-adic geometry of the curve. And they associate the cluster picture with other p-adic geometry invariance elements. So they are Berkovich skeleton, the spatial fiber, and the reduction map. And they use this, this comparison to prove what they need. So for example, if you have a curve which has this cluster picture at a prime L, and the leading coefficient of that curve is a unit, then they can claim that the local height of any of the QL point on X is 0. And that's the data they need in order to do some quadratic Chaboty. So this is really much an application of using the core of the cluster picture machinery, if you want. A more algorithmic application is this one. Here we start with the knowledge of the reduction. In this case, we have a genus 2 curve, and we fix a prime, which is odd. And we know that the curve has bad reduction at that prime, while its Jacobian has good reduction. So we start with already the knowledge of the reduction, and we want to compute the Euler factor. So we want to compute this AP value to compute its L function. And here we use again the classification. Because we know the reduction type, we also know, by reverse engineering again, we also know which pictures will occur for those curves. And then we build an algorithm which is based on those pictures. If this is this picture, then the local factor is this. If this is this picture, the local factor is this, and so on. And it's genus 2. This technique works well because we only have to consider 4 possible cluster pictures. In this particular application, what we use here is the explicit nature of the cluster picture machinery. So, for the modular method, one key step is to understand the conductor exponent of the Jacobians of the curves. So, these are families of hyperelliptic curves. They depend on 3 parameters, R, A, and B. When R grows, the degree of the polynomial grows and the genus of the curve grows. And what we exploit here is the fact that these families are very explicit and you can extract the roots. So once you have the roots, of course, you can do the clusters. And once you have the clusters, you can compute the conductor exponent using the machinery that goes behind it. So this was, we've done this with quite a few families, and this was, to be honest, a bit of a surprise. I didn't know that we could work with clusters on families of curves. But of course, it turns out that if your family is nice enough that you can extract your roots, then you can run this cluster machinery on them. And the last one, which is an example of this reverse engineering method, is this work by Annie and Dockschitzer. So here, they want to produce hyperelliptic curves of any genus with a specified Galois image. So they want to produce they want to solve the inverse Galois problem for this particular group. And what they have been using here, among other things, of course, I mean, I'm just extracting one step of their work, but when the prime L is not equal to P, then they use the fact that this cluster machinery understands the p-adic representation of the curve just because it's explicitly indexed on the type of clusters and some characters that can be extracted from the cluster picture. So here the key point is the radius of the clusters. Really the data of how Galois acts on the roots is essential here, and it's captured in the radius of that cluster. Okay, so this is pretty much all the applications that I meant to present for hyperelliptic curves. And now we need to step into the general case. So let me remind you that we went from something quite nice to something quite complex. That's a genus 3 non-hyperelliptic. I can't present examples of many non-hyperelliptic curves, but I want to emphasize that for hyperelliptic curves, you could have guessed, if you understood the elliptic curve case, you could have guessed that the roots of the polynomial were containing enough information if you understand how they are p-adically. But for general curve, it's unclear what data we should extract from the curve. So the honest answer is that we don't know. So given a general curve, we don't know where does this minimal data sit, which I called in this title when I said the essence of curve. This is what I meant. Given a curve, what do you need to extract to really capture all the p-adic geometry of that curve? And for general curves, it's a very fascinating and active research area, but I think it's fair to say that it's still open at the moment. But I should mention some work on genus 3 by Van Bommel, Docking, Dockschitzer, Lercier, and Lorenzo Garcia. So here, what they chose to look at was not the roots, because there is no such a thing. They look at non-hyperelliptic genus 3, but they've conjectured that there exists an equivalent classes of bitangents of the genus 3 curves, which can be the equivalent of the roots of the hyperelliptic curve. So those are Cayley octads, and they have a paper where they conjecture that understanding the valuation of those Cayley octads is really recovering all the data that I showed for hyperelliptic curves. So namely, you could reconstruct stable models and possibly regular models as well. But again, this is very much an active research area at the moment, but it's I guess we are quite hopeful that this is the right way. But this is genus 3, right? And for higher genus, we'll be back to square one, I guess. So the essence for general curves, I think, is still to find. And I find this problem absolutely fascinating. I should say that we have quite a few algorithms, nonetheless. For general curves, there have been some work, some a long time ago and some more recently. So Tim Dockschitzer and himself and Muselli, they have some algorithms for general curves with some conditions on the prime, Wevers and Austin as well. And of course, Magma has this implementation of the function regular model, which may or may not gives you a regular model. So algorithmically, there is some ways to access the local arithmetic of the curve. And even though it's not a theory, it's not a complete theory, at the moment, it will certainly help. Because again, remember BSD, at first it starts with data. It starts with, can we compute things and test? And we have quite a few tools at the moment to test, which is very, very nice. Okay, so that's for general curve. And just to finish, I need to remind you of something. We discussed local to global, and the first thing was to understand the local theory of varieties over QP, but for all P. And one thing that I nicely brushed under the carpet is the fact that nothing I said worked at 2. So 2 is significantly more annoying, although fascinating as well. But what do we know of p-adic theory of curves? Elliptic curves are well understood. For hyperelliptic curves, there are mixed results. We have some theoretical results using clusters. That's the work of Dockschitzer and Morgan. But then it's when the curve has ordinary good reduction. And there is some possibility to extend this, but it's still, again, active research. The work of Yelton and Yelton-Fiore. The new work of Geringer and Pink and Geringer himself. This is on stable reductions at 2, and also algorithms by Wevers and Austin, and algorithms by Liu. So here again, we have a lot of tools to work with. So it's also, I think we can say that we're very hopeful that we will be able to understand this p-adic theory of curves a bit better for hyperelliptic curves. General curves, of course, are a bit more difficult, but as I mentioned, we have some algorithms. So Dockschitzer's algorithm works in some cases, and also Magma as well. So we have some things to work with, and I hope that it will lead to new work. I think I will stop here, and I thank you very much for your attention.
Okay, questions, please.
Hi, Celine. Thank you for a really interesting talk. I guess my question was about whether these cluster pictures really define a curve uniquely. So if you had local information at every prime or for these set of primes, you knew exactly what the cluster pictures looked like, and you reverse engineered a curve from that information, would you get, finitely many, just one, infinitely many curves with that local data?
Over Q, you mean?
Yes.
Oh, no. So do you want to produce a curve over QP, or you want to produce a curve over Q?
Really over Q, so you're looking at the cluster pictures at
all primes, you have a cluster picture and you want to... Yes, you can do this, and that's what Annie and Dockschitzer did. They really... You basically locally approximate your roots globally, so that they behave. It's a Chinese reminder theorem.
And it uniquely determines the curve?
Sorry?
Does it uniquely determine this curve?
I don't think so. Because you have some flexibility at... Yeah, you have some... Yeah, I don't think so.
Okay, thank you.
Hi, thanks for the talk. Since hyperelliptic curves are possible to deal with using cluster pictures, and the non-hyperelliptic curves are very difficult, have people tried to look at superelliptic curves as a sort of intermediate ground for generalizing this? So y to the n equals f of x.
Yes, for algorithmic work. In fact, the algorithm I talked about by Liu and Wevers and Austin There are more that I haven't mentioned, but they do compute the local behavior of superelliptic curves. In theory, you mean using clusters, a classification like this? No. But yes, that could work.
Is it already implemented in databases, superelliptic base?
It depends what database and what algorithm you mean. There are some algorithms, there are some databases. Where is a different question. How to access them is different. I don't know.
Okay. More questions?
Well, thank you. First of all, your beautiful talk. So, in this cluster picture approach, the input is a polynomial, but what we care is just all about the roots and how the relationship between them, right? So, in your algorithm, do you need to factor your polynomial, or is there a way to draw these pictures without factoring your polynomial? Without it can be very hard, especially for complicated polynomials.
Yeah, thanks. That's a great question. The straight answer is yes. If you can factorize, you can do it. If you just need the cluster and you don't need the roots, there are ways to compute the cluster without going to the splitting field of your polynomial. So that's if you need only the cluster, you don't actually need to know the root. If you actually for the cluster as well, there are some recent work where they are trying to reproduce they're trying to reproduce Tate's algorithm for hyperelliptic curve. Namely, given the coefficients, can you work from the coefficient to get the cluster? And there are some positive answers. How much it's efficient, I don't know, but there are ways to do this. Yeah, I can give you references. The name is just. Yeah, so
Yeah,
I forgot the name.
thank you. Thank you.
So I was wondering about your kind of cluster classification, because it's a really combinatorial description and it's related to valuations. So it reminds me of tropical geometry. So I was wondering if it fits into that framework, if it was a special case, or if it had some relations with this whole area of math.
Well, I think yes, it does relate to this. First, because if you quotient this cluster picture by the hyperelliptic involution, you get a tree. And so that's one relation. The second is also the quadratic Chaboty method I mentioned, where you've seen there was this Berkovich skeleton. So again, you can relate it to different setting, is what I'm trying to say. Whether it's directly relating to tropical geometry, I'm not certain, because I'm not an expert at all, but possibly, yeah.
Okay, thanks. Maybe a more concrete question. It's not equivalent having the same cluster structure and defining equivalent tropical curves, for example.
I don't know.
Okay, thanks.
So, given a cluster, is it possible to say how many curves are there? Like,
How many?
curves are there with the same cluster? Like, for example,
How many curves are there with the same clusters? Infinitely many.
but if you take two different clusters, so is it possible to say, I mean, both of them might, is there any case where they can have finitely many curves?
Is there a case of a cluster where there is only finitely many curves with this cluster?
Yes.
No. Simply because if you give me a cluster, I'll be able to construct an infinite family of curves satisfying this.
Thank you very much for your very interesting talk. You mentioned at one case, at one part, the genus 3 case, non-hyperelliptic. Is there an odd residue characteristic for non-hyperelliptic genus 3 curves? Maybe some general description of possible reduction types?
So non-hyperelliptic,
Genus 3.
genus
So for
3.
really smooth plane quarters.
Yeah. So these octaves, the KD octaves I mentioned, are the possible equivalent of cluster picture in this case.
And then does there really exist an equivalent sort of full classification?
Yes. So yeah, you should have a look at the paper. I don't know if the slides are accessible, but I can send them to you. But they have a beautiful picture of stable reductions in genus 2, conjectured from the valuation of the KV octaves.
Thank you.
Okay, maybe I'll ask the last question. So this case of p equal to, yeah, when you have wild multiplication, of course it's more complicated, but there is now going to be extending by Weber's and how critical it is for your global applications, for example. But you mentioned just one prime.
Oh, no, but that's the key point. Because you want to do some local to global, you really need, when you take the product over all primes, you need 2. So at the moment, we're a bit stuck when we take the product over all prime, because, I mean, I talk for myself, but I'm sure I'm not the only one. We have to divide a very specific case at 2, because we want usually good ordinary reduction, because this is where it's very nice.
I see. So people with from wild application that you come to you with some suggestions, you need.
Absolutely. If you have suggestions, that's
Okay.
always
So let's thank Celine.
Just a word about the rest of the program today. We do it exactly like yesterday. So now there's a lunch break, and then at 1:45 we have the parallel sessions. I'd just like to remind everybody that we want to stay synchronized, so please stick to the 20 minutes talk plus at most 5 minutes question, so that it works as smoothly as yesterday. Then we also got the question already about details for the excursion tomorrow. And I think we're just going to announce this tomorrow morning. Then you'll know exactly, for those who chose to go to the case mates, how to get there. I can already tell you we'll go there by train, but the train times and so on, these details, they will be announced tomorrow. Okay, then enjoy lunch.